Hospitals are integrating generative artificial intelligence tools to automate medical reports. These systems use algorithms trained on massive datasets to generate new text or images. While these models can pass written medical board exams, selecting the correct text for a multiple-choice question is a distinct task from interpreting the complex grayscale pixel data of a raw patient radiograph. Assuming all large models possess the same reasoning capabilities is a risk in clinical environments. In radiology, the specific architecture of a model dictates its diagnostic utility. 3 architectures are tested for radiograph interpretation. General-purpose models learn from broad internet data. Domain-specific models train exclusively on medical images. Agentic models operate as coordinators, delegating tasks to subtools. A recent study compared 4 models representing these paths: Gemini 2.5, Mera-2, Rad.1, and MedRAX. Investigators tested these 4 systems against each other to analyze how their different structures perform when faced with real human patients. Examining these architectural differences allows us to separate actual clinical utility from uncalibrated technological hype. The study utilized 212 consecutive frontal chest radiographs pulled from a teleradiology service covering secondary hospitals in the United States. The researchers enforced a zero-shot constraint, meaning the models were given the task without prior examples or context. They received only the raw image, no patient history, clinical notes, or prior exams. 3 independent human radiologists with up to 7 years of post-training experience conducted a blinded review of the AI-generated reports. The human readers scored the outputs based on 2 metrics: a binary measure of whether the report was acceptable without modification, and a holistic clinical quality score from 1 to 5. By removing all supporting text, this methodology strips away the AI's ability to guess based on written context, forcing the architecture to rely on pure visual diagnostic reasoning. The grading data showed that the general-purpose model, Gemini 2.5, struggled with clinical acceptability. The human radiologists rejected Gemini's reports approximately 80% of the time. Individual acceptability scores across the 3 readers were 16, 18.4, and 35.8%. This scatterplot compares sensitivity against specificity. Gemini achieved a pooled sensitivity of 50.6%. Training on the broad data of the internet does not equip a model to interpret the hyperspecific grayscale patterns of a medical X-ray. Fine-tuning is often proposed as the solution. Mera-2 is a domain-specific model trained exclusively on medical data. On the scatter plot, Mera-2 achieved a high specificity of 96%, correctly identifying healthy patients, but its sensitivity dropped to 35.5%, missing the majority of actual diseases. Single-pass neural networks often face a trade-off, either guessing too frequently or becoming too conservative to be clinically useful. Rad.1, an agentic vision language model, emerged as the most successful system in the clinical acceptability test. It was the preferred model for all 3 human readers, reaching an acceptability rate of 75.5% without requiring modification. This performance is tied to its agentic architecture, which acts as a coordinator rather than attempting to process the entire diagnostic task in one step. In this pipeline, a central node delegates the analysis to specialized subtools. It sends the image to a classifier, verifies data with a retriever, and synthesizes the findings into a report. This modular approach mirrors human clinical workflow, examining visual evidence, referencing medical parameters, and then drafting a conclusion. On the scatter plot, Rad.1 shows a significant jump in performance, balancing 66% sensitivity with 94.6% specificity. This architecture succeeds by leveraging dedicated classification tools for specific tasks, rather than relying on the generalized logic of a single network. Breaking the diagnostic process into coordinated subtasks provides a viable path for automated radiograph interpretation. We can see how these structural differences manifest by looking at how each model handles a specific patient radiograph. This frontal chest radiograph contains a specific, life-threatening finding. The ground truth is a subtle, small to moderate left pneumothorax, indicated here by the black arrow. These are the reports generated by the 4 models for this identical image. The generalist and domain-specific models both failed to detect the pathology. Gemini stated no pneumothorax is seen, and Mera-2 reported the lungs were clear. These models produce confident, structured text that can mask a complete failure to identify a collapsed lung. Now we can look at the output from the agentic model, Rad.1. Rad.1 correctly identified the disease, flagging a minor apical pneumothorax. However, Rad.1 incorrectly identified the location, stating the pneumothorax was on the right side instead of the left. While agentic models are better at detecting anomalies, these struggles with spatial reasoning mean they are best used as assistive tools within a human-in-the-loop workflow. The performance of one agentic model does not guarantee the safety of the entire architectural class. MedRAX is the second agentic model in the study, using multiple analysis tools integrated with multimodal reasoning. The data reveals a massive disparity in hallucination rates. While Rad.1 maintained a rate of 5.7%, MedRAX spiked to 53.8%. In a radiological context, a hallucination occurs when the AI fabricates clinical statements that have no basis in the inputted pixel data. A second test case demonstrates the potential consequences of these fabrications. The MedRAX report for this image begins by referencing a comparison with the prior study. The model was provided with no prior studies. It confidently invented a past exam to justify its interpretation. An advanced agentic framework does not inherently ensure reliability. If the internal component tools are poorly calibrated, the system will confidently invent clinical history. Evaluating 212 consecutive patient scans clarifies the current limitations of medical AI. Single-pass generative models are currently unable to provide reliable zero-shot radiograph interpretations. Coordinating specialized subtools through agentic workflows is the necessary framework for medical analysis. The performance gap between Rad.1 and MedRAX indicates that the agentic approach requires precise, validated execution to be safe. Rigorous, task-specific benchmarking of every individual component is required before these systems can be integrated into clinical environments. In high-stakes radiology, healthcare systems must look past the output and demand to see exactly how a model's internal architecture arrives at a diagnosis.